Good evening, ma'am.
Good evening.
Hello, ma'am.
Good evening, sir. You can start now, sir.
Okay, ma'am.
Good evening, sir. Good evening, sir.
Good evening. Good evening. Yesterday, we were learning about the nomenclature of the coordination compounds, and we have also started with isomerism, and we finished structural isomerism. Just to have the continuity, we will revise different types of structural isomerism. Now, I'll go fast in explaining the structural isomerism. Now, the first one is called as ionization isomerism. What is this ionization isomerism? We took an example yesterday. CO, cobalt is the metal, NH3 5 times, SO4, Br. And we also took one more compound, CO, NH3 5 times, Br and SO4. For both these compounds, the molecular formula is same because both contains one cobalt atom, 5 ammonia molecule, 1 sulfate and 1 bromine. But what happens is when we dissolve this in water, they dissociate to give different ions. This will dissociate in water to give SO4 minus and Br plus, Br minus. This is SO this complex plus. And this one you will get CONH3 5 times Br 2 plus, and we'll get SO4 2 minus. So ions are different. So what is ionization isomerism? Coordination compounds having same molecular formula, but they ionize in aqueous medium or they ionize in water to give different ions is called as ionization isomerism. You followed with this?
Yes, sir.
The next one is linkage isomerism. I told you linkage isomerism is possible only when we have ambidentate ligand. What is ambidentate ligand? Ligand which can get bonded to the central metal atom in more than one way is called as ambidentate ligand. Now for an example, CO, NH3 5 times, NO2, and we can write maybe Cl2. This is an example. Now, this complex, if you write, the coordination number of this complex is 6 because we have 6 monodentate ligands. So number of monodentate ligands bonded to the central metal atom is called as coordination number. Whenever the coordination number is 6, it will have octahedral structure. It will have octahedral structure. We can represent octahedral structure like this. 5 ammonia molecules we can represent like this. And this NO2, I'm representing it like this. This is the first structure. So the charge is 2 plus. The second structure I'm writing here, cobalt, it also has 6 coordinate bonds. This arrow indicates a coordinate bond. 5 ammonia molecules, we write 5 ammonia molecules like this. Because nitrogen is a donor atom, therefore the line has to start with nitrogen. So this is NH3, and I write here it is ONO, and this also has a charge 2 plus. See, this compound has same molecular formula, same structural formula, but they differ in the mode of linkage. Now here it is linked through nitrogen, here it is linked through oxygen. So NO2 minus nitrito ion is a ambidentate ligand. It can get bonded through nitrogen or it can get bonded through oxygen. So linkage isomers are compounds, coordination compounds having same molecular formula, same structural formula, but the mode of linkage between the ligand and the central metal atom is different. Those are called as linkage isomerism. Did you follow this?
Yes, sir.
Coming to the third is hydrate isomerism. Now, hydrate isomerism are coordination compounds having same molecular formula, but they will have different number of water molecules as the ligand. When they have different number of water molecules as the ligand, then they are called as hydrate isomerism. Now, for an example, if you take CO, H2O 6 times and Cl3, there are 6 water molecules as the ligand. If you take CO, H2O 5 times, Cl, and you have Cl2 dot H2. See, you can see the molecular formula for both the same. 1 cobalt atom, 6 water molecules, 3 chlorine atoms. Molecular formula same. But in the first case, we have 6 water molecules as ligands. And in the second case, we have 5 water molecules as ligands. Therefore, this kind of isomerisms are called as hydrate isomerism. What do you mean by hydrate isomerism? Coordination compounds having same molecular formula, same structural formula, but differ in the number of water molecules as the ligand. Those are called as hydrate isomerism. Next, the last we learned is coordination isomerism. Now, this coordination isomerism is formed by the interchange of the ligands between the complex ions. Now, for an example, I have cobalt and chromium, cobalt and ammonia 6 times, and chromium and cyanide 6 times. This is the first set of example. The second is interchange. So cobalt will undergo the interchange of ligands. So cobalt will get bonded with cyanide and chromium will get bonded with ammonia. So the ligands gets interchanged. Those kind of isomerisms are called as coordination isomerism. Isomerism in which the molecular formula is same, but the ligands get interchanged with the metals. Those kind of isomers are called as coordination isomerism. So these 4 isomerism, what we learned, they are all example for structural isomers. They're all example for structural isomer. Did you understand this? Can we go further? Are you there?
Yes, sir. Yes, sir.
Now, today we're going to learn. You need a lot of imagination to understand this. All right. This isomerism, what we're going to learn today, is called a stereoisomerism, or it is also called a space isomerism. Stereo stands for space. Now, space, in the sense, it's a 3-dimensional arrangement of atoms or molecules. So it is not a 2-dimensional representation. Space is a 3-dimensional representation. X, Y, and Z axis will be there. So what is stereoisomerism? Compounds, coordination compounds having same molecular formula, same structural formula, but they differ only in the spatial arrangement of atoms or group of atoms about the central metal atom. Those are called as stereoisomerism, or they are called as space isomerism. What do you mean by stereoisomerism? Coordination compounds having same molecular formula, they will have same structural formula, but they will differ only in the arrangement of atoms or group of atoms in space. Those are called as what isomerism? Stereoisomerism. Did you follow what's the definition of stereoisomerism? Stereo stands for space. So compounds will have same structure, same molecular formula, but only the difference is the arrangement of atoms or group of atoms in space. We will take example, then we will understand. The stereoisomerism is of 2 types. One is geometrical isomerism. This geometrical isomerism is also called a cis-trans isomerism. The other one will be called as optical isomerism. This geometrical isomerism learn now. Optical isomerism we will try to understand a little later today. Now, what is this geometrical isomerism? Geometrical isomerism, or it is also called as cis-trans isomers. Now, stereoisomers definition I gave you. Coordination compounds having same molecular formula, same structural formula, but differ only in the spatial arrangement of atoms, only differ in the arrangement of atoms or group of atoms about the central metal atom in space. Those are called as geometrical isomerism. Now, two types I told you. The first one is cis-trans isomerism. These isomerism arise due to the difference in geometrical arrangement of ligands around the central metal atom. So this cis-trans isomerism arises, or it formed due to the arrangement of atoms or group of atoms or ligands around the central metal atom, difference in the arrangement of ligands around the central metal atom. We will take an example, we will understand that. When identical ligands are occupying this position near to each other, they are called as cis isomer. When identical ligands occupy the opposite side positions, they are called as trans isomers. This is very common in di-substituted complexes with coordination number 4 and 6. Can anyone tell me what is coordination number? What is coordination number? Please tell, what is coordination number? Number of monodentate ligands bonded to the central atom.
Yes, sir.
Called as coordination number. What?
So it's the same thing, sir. I was gonna say.
Same thing. When I ask, you don't tell. When I complete, you say same thing. All right.
So no, sir. Like just thinking
All
around.
right. This is a compound. Okay, fine. This is a compound. We have taken this as an example now. Now, coordination number of platinum is 4. Why? We have 4 ligands here, 2 ammonia and 2 chlorine. Since we have 4 ligands, the coordination number of platinum is 4. So we learned that geometrical isomerism or cis-trans isomerism is observed in di-substituted complex of coordination number 4 and 6. So complexes with coordination number 4 and 6 will show cis-trans isomers. Now, for this molecule, PT, NH3, twice Cl2, I will write PT. I will write coordination compound. It's a square planar complex. We will learn the structure a little later. Now, you have to understand what is square planar complex. Now, you should remember, if you have a notebook with you, at the center of the notebook, you will have what? At the center of the notebook, this is a notebook. At the center, you will have what? Metal. At the 4 corners, you will have ligands. This will be called a square planar structure. Metal is at the center, and you can see 4 corners of the metal. So this 4 corners, you will have ligands. Those are called as square planar structure. Now, in case of this molecule, now if I write ammonia, here also ammonia, here chlorine and chlorine. You can see chlorine is close to each other, and here ammonia is close to each other. Therefore, this isomer will be called as cis isomer. All right. Now, if I write a platinum here and 4 coordinate bonds like this, and here is ammonia, here it's ammonia, here it is chlorine, and here it's chlorine. So ammonia is what? Far away from each other. Chlorine is far away from each other. These kind of isomers are called as trans isomers. Now, if you observe, when identical ligands occupy positions opposite to each other, is called as trans. See, ammonia is opposite, chlorine is opposite, therefore it's trans. When identical ligands occupy near to each other positions, they are called as cis. Ammonia is close to each other, chlorine is close to each other. This is called as cisplatin. Cisplatin. This is the compound which is used for cancer treatment, cisplatin. And this is called as transplatin. The IUPAC name is different, and the common name for this is cisplatin and transplatin. The cisplatin and transplatin has square planar geometry. Square planar geometry, square planar structure. So coordination number 4 compounds can also have tetrahedral geometry. When the coordination number is 4, they can also show tetrahedral geometry. When they show tetrahedral geometry, in all 4 ligands are symmetrically arranged with respect to one another, such geometrical isomerism is not possible. Even though coordination number is 4, If a complex shows tetrahedral geometry, it will not show cis-trans isomerism. It will not show geometrical isomerism, or it will not show cis-trans isomerism, because in tetrahedral geometry, all the ligands will be what close to each other. It's in three-dimensional space. You have to view it. All right. So all will be in close to each other. All will be arranged symmetrical to each other. Therefore, even the coordination number 4, tetrahedral complexes will not exhibit cis-trans isomerism or geometrical isomerism. Did you follow the students?
Yes, sir.
Ask you why tetrahedral geometry will not show, or tetrahedral complexes will not show cis-trans isomer. You should answer. They will not show cis-trans isomer because all the ligands are symmetric with each other, close to each other. Therefore, they will not show cis-trans isomerism. So with coordination number 4, only complex having what structure? Square planar structure. What do you mean by square planar structure? A notebook is a rectangle, but assume it to be a square. And all the atoms are present in the same plane. When all the atoms are present in the same plane, they will be called as square planar structure. Followed?
Yes, sir.
Yes, sir.
Yeah. Coming to the next, coordination number 6. Coordination number 6. When the coordination number is 6, they show what geometry? Again, they will show what? Cis-trans or geometrical isomerism. Now see what is there here. Square planar geometry. I explained already. Square planar geometry. 4 ligands occupy the position of 4 corners, and the metal atom or ion at the center, and they lie in the same plane. Ma2B2 type. Ma2B2 type. Metal. See, this is a different example. I told metal A2B2 type. A is a ligand, B is a ligand. I gave you platinum, I gave you NH3 twice, and I gave you Cl twice. I took the example for this to explain. And here they have taken a different example. They have taken chlorine, platinum, chlorine, ammonia, and pyridine. Py stands for pyridine. Pyridine is also a monodentate ligand. All right. Now you can see this is wrongly, this is not clearly mentioned. So anyway, this is platinum, this is platinum. So don't worry about this example. Cisplatin, you remember. Or this example also you can remember. If pyridine is close to, now if I write like this is platinum and 4 bonds, and pyridine is close to each other, chlorine and ammonia. This will be what? Cis isomer. If you take platinum, and if pyridine is opposite, py, ammonia, and chlorine. So this will be what isomer, trans isomer. Did you follow this?
Yes, sir.
Yes, sir.
Yeah. Now coming to the complex with coordination number 6. When the complex is coordination number 6, it will show octahedral geometry. It will show octahedral geometry. What do you mean by octahedral geometry? You know what is square planar. What is square planar? In a square, the metal is at the center, and 4 corners, we have 4 ligands. This is a ligand, this is a ligand, this is a ligand, and this is a ligand. So in case of octahedral geometry, this is square planar. One ligand will be above the plane, the other ligand will be below the plane. Then this geometry is called as octahedral geometry. Can you visualize? Can you visualize?
Yes,
You have a notebook, 4 corners, 4 ligands, center metal, above one ligand and below one ligand. That will be the representation of what? Octahedral geometry. Are you able to visualize that?
Yes, sir.
Now you have 6 positions. See, when we say 6 positions in octahedral geometry, so I can write 1, 2, 3, 4, 5, and 6. Now you can see cis position. If you have 1 and 2 close to each other, cis. 2 and 3, they are also what? Cis. 3 and 4, they are also cis. 4 and 5, they are also cis. And 5 and 6 should also be what? Cis. So whenever the ligands, when I say similar ligands are in the position 1, 2, or 2, 3, or 3, 4, 4, 5, or 5, 6, then that will be called as what position? Cis position. When we say transposition, if the ligands are present at the first position and the fourth position. See, first and the fourth position. One is above the plane and one is below the plane, opposite. That will be called as transposition. Now, this is second position and the fifth position. You can see it's in the opposite. 2 and 5, it is called as transposition. And 3 and 6, opposite, transposition. Did you follow this, students? When
Yes,
we
sir.
will call cis and when we will call trans, do you understand? So if the similar types of ligands are present in 1, 2 position, or 2 and 3 position, or 3 and 4 position, or 4 and 5 position, or 5 and 6 position, they'll be called as cis. It is 1 and 4 position, trans. 2 and 5 position, trans. 3 and 6 position, trans. I hope that you followed. Yes. Now just see the example here. Now, X is a ligand, type of ligand. So this is an octahedral complex. You have a metal, and you have a metal, and you have L4X2 type. This is of the type ML4X2, or they write it as MA4B2 type. That means A is a ligand, B is a ligand. A we have 4, B we have 2. Those are called as what? MA4B2 type. Now in MA4B2 type or ML4X2 type, see X. Now if I number this 1, 2, 3, 4, 5, and 6. See 5 and 6. X is close to each other. Therefore it will be what? Now if you observe here 1, 2, 3, 4, 5, and 6. 1 and 4 in the opposite direction. Therefore it will be trans. Did you follow this, students?
Yes, sir.
So octahedral geometry coordinate. See, this is we're talking about geometrical isomerism. Geometrical isomerism is also called a cis-trans isomerism. Coordination compounds with coordination number 4 and coordination number 6 will show cis-trans isomers. So we learned with coordination number 4 in detail. Now coordination number 6 we are learning. Now some of the examples they are mentioning here. See, one we learned MA4B2 type or ML4X2 type we learned. The example is COCl2 NH3 4 times plus. This is an octahedral complex. If I write like this, octahedral complex. So this is CO. I have Cl, I have Cl, and all these are now ammonia. What type of isomerism is this? What type of isomerism is this? The charge is plus. What type of isomerism is this? Cis or trans? Cis or trans?
Yes, sir.
Huh? Cis or trans?
Sir, this will
Sir,
be,
this, sir.
sir.
Chlorine is close to each other. All right. Therefore, it will be what? Cis. Now, if I write trans, now I can write like this. I will write here. I have a square planar. This is cobalt. And I have ammonia here. Here also ammonia. Here also ammonia. Here also ammonia. And here it is chlorine and here it is chlorine. Chlorine is on the opposite side. Therefore, it will be called as what? Therefore, it will be called as what isomer? Trans isomer. Did you follow? This is of the type what? MA4B2 type or ML4X2 type. See, you have to remember this. Types of isomerism possible in coordination number 6. Students, did you follow?
Yes, sir.
The next type of isomerism, we are learning the coordination, what's it, cis-trans isomerism only. In that, we are learning different type, that is A3B3 type. A and B are ligands. So 3, we have A and we have 3B. So metal is rhodium and A is chlorine and B is pyridine. So they have given rhodium complex. RH is rhodium and PY is, this is the complex. Now, when we say this is the complex, you can have rhodium at the center. Octahedral is a structure. So I can write chlorine here and ammonia here. See, this is a square planar. Here, this is. Now you can see these chlorine atoms are close to each other. Therefore, this will be called as what isomer? Cis isomer. See, they have mentioned this geometry here. this for different complex they mentioned. Okay. So this will be called as what? Cis isomer. And if I have to write the trans isomer, I can write chlorine is here. And one more chlorine I can write. Ammonia, ammonia, ammonia here. And I can represent this chlorine on the opposite side. Therefore, no, maybe, yeah, opposite side. Therefore, I can call this as what isomer? Trans isomer. This is of the type EMA3B3 type. Did you follow?
Yes, sir.
Yeah. The third type of complex is MAA twice and EN twice 2 plus. AA is a bidentate ligand. This is wrong. This is wrong. Anyways, I'll give you this representation in a few minutes time. We will see. It is not MAA2, it is MA2 EN twice. So it should be like that. Now this is MA2 EN2 twice. EN is a bidentate ligand, remember. So they have given you a cobalt complex, cobalt, and A can be chlorine, Cl2, and En twice. Assume that this is the complex. So cobalt is at the center and octahedral structure because the coordination number, what will be the coordination number of cobalt here? What is the coordination number of cobalt?
So 6, sir.
It is 6 because ethylene diamine is a bidentate ligand. 2 into 2 is 4 and 2 chlorine atom. Therefore, it is 6. Now I write one ethylene diamine like this. The second ethylene diamine I write like this, and chlorine I write like this. See? Now, what isomer this will be? Ethylene diamines are close to each other. Chlorine are so close to each other. Therefore, it will be cis isomer. Now, the next isomer you see, and then you will understand better. I write this is En, and here it is En, and I write chlorine. What isomer this will be? Trans. Chlorine is in the opposite side. Even ethylene diamine is in the opposite side of cobalt. Therefore, this will be called as what isomer? Trans isomer. So we have learned in detail with geometrical isomerism, with coordination number 4 and with coordination number 6. So if the ligands are close to each other, then they are called as cis isomer. If the ligands are opposite or far away from each other, opposite to the metal, they are called as trans isomer. Followed?
Yes, sir.
Yeah. Now, others, students, are you there? Anybody else has any clarification? Yeah.
No, sir.
No. All right. Now coming to the optical isomerism. Optical isomerism. All right. What is the condition for a molecule to exhibit optical isomerism? Now, assume, I don't know, don't laugh. This is a left hand. This is my left hand. This is my left hand. And I keep a mirror. This is my thumb. This is my little finger. I keep a mirror here. Now, thumb will be here in the mirror, and this is a small finger. This is small finger. This is a thumb. Yes or no? It will appear like this. Yes or no?
Yes, sir.
Yes. Now, if I place the left palm, listen to this, left palm on my right palm, are the fingers superimposable?
Yes, sir.
Oh, where must superimposable? Keep your left palm on the right palm and see.
So no, sir. It's
Thumb
overlap.
is in the
Yes, sir.
opposite or not?
direction. Opposite, sir.
Small finger is also opposite. Yes or no? Don't keep your fingers as if you're making namaste. No, it's not like that. I'm asking to keep one palm on the other, on the top.
Then it will be not, sir.
That is called as non-superimposable mirror image. They are called as what? Non-superimposable. See, if I keep my left arm in the mirror, it appears like a right arm. But if I keep my left palm, sorry, not arm, left palm over the right palm, are they superimposable? They are not superimposable. So if a complex are mirror images of each other, But if they are not superimposable on each other, those kind of molecules or coordination compounds will exhibit optical isomerism. What is the chirality? You would have learned it in organic chemistry, something called as chirality, chiral carbon atom or something. Now, here in coordination chemistry, if a molecule has to exhibit optical isomerism, the complexes should be having mirror images of each other. But the mirror images should not be superimposable. They should not be superimposable. If I keep one molecule on the other molecule, they should not be what? Superimposable. That is the condition for optical isomerism. Now, what is this optical? Optic stands for? Optic stands for light. Now, what is this optical isomerism? Optical isomerism are compounds having same molecular formula, same structural formula, but differ in the rotation of plane polarized light. If the plane polarized light is rotated right side, it is called as dextrorotatory. If the plane polarized light is rotated left side, it is called as levorotatory. Have you heard of these terms? Dextro and levo in
Yes.
organic
Yes.
chemistry? Yes. Now, see, this is coordination chemistry. In case of coordination chemistry, if a molecule have to exhibit optical isomerism, the molecule should have same molecular formula. They should have same structural formula. They should be mirror images of each other. But that mirror image should not be superimposable. The mirror images should not overlap. Those, right, the proper word is superimposable only. Don't use overlap. So non-superimposable mirror images. So that is the condition for optical isomerism. Now, what is optical isomerism? You can see the points, what's been mentioned here. Optical isomerism are mirror images of each other and have chiral. So they have chiral. Chiral, we'll learn about chirality. Now, optical isomers are mirror images of each other, and mirror images should not be superimposable. This is the important condition. This is the criteria for a coordination compound to exhibit optical isomerism. The mirror images should not be superimposable and do not have plane of symmetry. And do not have plane of symmetry. What is this plane of symmetry? If I draw a sphere here, if I draw an imaginary line like this imaginary line cuts the sphere into two equal halves, yes or no?
Yes, sir.
This is called as plane of symmetry. An imaginary line which divides the compound into two equal halves is called as plane of symmetry. So any molecule, a coordination compound, they should not, what is superimpose and do not have plane of symmetry. They should not have, do not have, it is not do and have, it is do not have plane of symmetry. That means the molecule should not be in a position to be divided into two equal halves. That's called as plane of symmetry. Now just observe. Optical isomers have similar physical and chemical properties, but they differ in the rotating of plane polarized light. So I told you, we'll learn what is plane polarized light in a few minutes time. All right. Now, optical isomerism have same molecular formula, same structural formula, but differ only in the rotation of plane polarized light. When the isomer rotates the plane polarized light to the right, it is called as dextrorotatory and called as D form. D stands for dextroform. And isomerism, which rotates the plane polarized light left, is called as levorotatory. It's called as L form. Example for the complex, it can have M, A2, B2, C2 type and En minus or plus. The charge can be -1, -2, -3, whatever it is, or +1, +2, +3. So we have three types of ligands here. You can say they are called as M, A2, B2, C2 type. Only those kind of molecules can exhibit one of the type of molecule which can exhibit optical isomerism. Now tell me, what will be the coordination number of metal here? What's the coordination number of metal here?
Sir, 6.
Yes, we have
Sir,
six.
sir.
Yeah, we have 6 ligands. Therefore, the coordination number here is what? 6. Now, example, you observe this. Example, you observe. Yeah. Yes. Now this is, I'll write it here. Let it be. So we will write chromium, NH3 twice, H2O twice, and we have Br twice and plus. This is the complex. The coordination number is 6. So the structure is octahedral. I will draw the structure like this. And I will write here NH3, NH3. I will write H2O, water, H2O. See what I've written here, H2O. I've written as OH2 because oxygen is a donor atom. And I write here Br, and this is Br. And I write this as a plus charge. And I write this as what? Plus charge. Now we'll place a mirror here. Now what will be the mirror image of this? What will be the mirror image of this? Let's see. The mirror image of this will be cobalt. We will have an octahedral structure. Ammonia will be close to the mirror, NH3, NH3. Water is here, OH2. Bromine will become away like this. This is again 2 plus. Now just observe this carefully. In case of this complex, ammonia is right side the cobalt. In case of its mirror image, ammonia is left side the cobalt. Now if I take this molecule and place on it, will they overlap on it? Will they overlap? Are they superimposable?
Sir, they will overlap.
Huh? Are they superimposable?
Sir, no, sir. Sir,
No, because
sir.
ammonia is right side here. If I take this and place, ammonia will be right side. But here in this complex, ammonia is on the left side. Bromine here is on the left side. Here, bromine is on the right side. Therefore, they will not superimpose it. So this is the condition for a molecule to exhibit what? Optical isomerism. There should be a non-superimposable mirror image. All right. So this is an example for a complex which shows optical isomerism. So optical isomers are compounds having same molecular formula, same structural formula, but they differ in the rotation of plane polarized light. So if the plane polarized light is rotating clockwise, so this molecule rotates the plane polarized light clockwise. Therefore, this will be dextro. And this will rotate anti-clockwise or the opposite side, anti-clockwise. Therefore, it is LEVO. Try to name this molecule. Try to name the IUPAC. Let's see now, someone name it. Let's see. What is the IUPAC name of this complex? We learned yesterday in detail. What is that? Cr, NH3 twice, H2O twice, Br twice, and plus. Tell me, what's the oxidation number of chromium? Chromium oxidation number is +3. Because as a whole, the complex is +1. Bromine is -1 into 2 is -2. Ammonia, water is neutral, ammonia is neutral, chromium we take it as X, so X will be equal to +3. What's the IUPAC name of this molecule now? Amine. This also starts with A, this also starts with A, aqua. AM, aqua, AQ. Second letter, M becomes before Q. So it'll be what? Diamine, di, aqua, dibromido, dibromido. What's the chromium? Chromium. What's the oxidation number of chromium? 3 ion. Chromium 3 ion. Did you understand the naming?
Yes, sir.
Yes, sir.
So you understand what is dextro and levorotatory? Yeah.
Yes, sir.
Now, if you take a
Yes, sir.
source, if you take a light, this light will scatter in all directions possible. And this white light, when you pass through a prism, the prism is called as nicol prism, NiCOL, nicol prism. All right. What happens is the light which is scattering in all the direction, they will be arranged in one single direction. This light is called as plane polarized light. This light is called as what light? Plane polarized light. So this plane polarized light, when you pass through the complex, how do you pass through this complex? This complexes are solutions. You have to take in a cuvette or in a container like test tube. It is called as cuvette. All right. And then this light is passed. And if you observe using a polarimeter, if the polarimeter shows clockwise rotation of this light, then it is dextro. And if it shows polarimeter shows anti-clockwise rotation, then left side rotation. Otherwise, it's called as levorotatory. You followed so far?
Yes, sir.
Now you can see there is a different type of complexes. Now all these are extra octahedral complex. Metal, and you can see A, B, C, D, E, different types of ligands. See, this different types of ligands. We have bromine, we have nitro, we have ammonia, we have iodine, we have chlorine, we have pyridine. Now, if you place a mirror here, they are mirror image. In this case, NO2 and ammonia is on the right side of the platinum. In this case, NO2 and ammonia is on the left hand side of the platinum. They will not have superimposable mirror images. So these mirror images are non-superimposable. So therefore, the condition is satisfied for the molecule to exhibit optical isomerism. This molecule rotates the plane polarized light clockwise, dextrorotatory. This molecule rotates the plane polarized anti-clockwise. Therefore, it is called as levorotatory. Did you observe? See, this is see, we learned earlier M, A2, B2, C2 type. Here we are A, B, C, D, E, F type. All the ligands can be different. And now we're going to learn something called as MAA3 type. MAA3 type, N plus or minus, it can be. Now, example they've given is cobalt En thrice. See, cobalt En thrice, what's the coordination number? 6. See, this is one En. This is another En. This is another En. And the charge is 3 plus. The charge is 3 plus. Now, this, if you place in the mirror, what will happen? You will get cobalt. What will be the, what you'll get? You will get En here, close by, and you will get this En here on the right side, and this En on the right side. See, these two En are almost on the left side of the cobalt. In the mirror images, they are on the right side. Are you following, students?
Yes, sir.
See, it is written here clearly. They are not. See, this is the actual structure. So they are mirror images of each other, but they are not superimposable. Therefore, this also will exhibit geometrical optical isomerism. All right, this is of the type MA3, AA3. What does this AA stands for? Bidentate. It is not A3. MAA3. AA is in the brackets. You can see. So it is a bidentate ligand. Followed.
Yes, sir.
Yeah. See, again, this is an example they've given. So we'll take an example like cobalt. Where is that? So cobalt, En twice, ammonia, and they've given chlorine 2 plus. This is the complex. We'll take one example. Examples given. This is of the type metal AA twice, AB, plus or minus, and the charge of the metal complex can be positive or negative. Now, since the coordination number, what is the coordination number for this? What's the coordination number for this?
That's 6.
Yes. Now, coordination number will be 6 and the structure will be octahedral. I can represent octahedral like this. En, I will write here 1. It's a bidentate ligand. That is why I'm showing like this 2 donor atoms. En is a bidentate ligand. And here I'll write ammonia and I will write Cl. This is 2 plus. If we keep a mirror here, what happens? It will look like what? It will look like cobalt. Here it is ammonia. and here it is chlorine, and here you'll have En, and here also you'll have En. So this will be the mirror image of this. Are they mirror image superimposable? You see, En is on the left side of the cobalt here, and here En is almost on the right side. Ethylene diamine is on the right side of the cobalt. Therefore, they are mirror images but not superimposable. Therefore, this also can exhibit optical isomerism. It can rotate the plane polarized light clockwise or anti-clockwise. Right? See, the same example here, they mentioned it as cis and transform also. Why they mentioned it as cis and transform? This En is close to each other, cis. Here En is on the opposite side, transform. So these kind of complexes, what are that? These kind of complexes, metal AA twice, C, B and C type, it can be plus or minus N type, can exhibit both optical and what? Geometrical isomerism. For what I'm telling, this is a complex with coordination number 6. This is exhibiting both what? Optical isomerism as well as what? Geometrical. If I place a mirror here, there will be mirror images of each other. But sorry, not this. This is not the mirror image. Sorry. So you can see this is not the mirror image. They have a different arrangement. So En is close to each other, cis. En is on the opposite side of the metal, therefore it is what? Trans. Followed?
Yes, sir.
Yeah. Now we'll have to solve with some of the questions. I don't know how many questions we can solve. Let us see. Let us learn some of the questions. Now just go through the topic optical isomerism, what we have done. Now, any clarification with that, you can ask me. Any
No,
clarification so far? No? Okay. Now, coming to the isomerism, we'll learn some of the questions. Few questions we'll try to learn and see whether time, it depends on the time. 10 minutes we have. How many geometrical isomerisms are there for CONH3 twice Cl4? How many geometrical isomerisms are there for CONH3 twice Cl4? That is octahedral, and AuCl2Br2 minus square planar. Here coordination number is 4, square planar. Here coordination number 6, octahedral. Now I will write the octahedral structure. How many isomers possible they're asking. So we'll write chlorine, 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 and here we'll write it as ammonia, and here also we'll write as ammonia. Now tell me what will be this isomer? This what will be this isomer? Can I call this as a cis isomer? Yes. Now coming to, see, they are clearly asking geometrical isomer. They didn't ask about optical isomerism. Now coming to the geometrical isomerism, if I represent like this, ammonia is here, Cl, 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 and Cl. So what will be this isomer called as? This isomer will be called as what? Trans.
Trans.
So they have, this molecule exhibits two isomers. One is cis and the other one is trans. Likewise, if you take gold is Au, sorry, Au. Square planar. If I represent Br, Cl, and Cl, what will be this isomer? Cis isomer.
Cis.
Chlorine is close to each other. Likewise, if I write, here it is Br, here it is Br, Cl and Cl, what will be this called as? Trans isomer. Artha, so did you follow?
Yes, sir.
What will be the option?
Option B.
So
Option
B, sir.
B.
Two cis.
So this will show two isomerisms, cis and trans, and this also will show two isomerisms, cis and trans. So hence the answer for this question is option B. The next one is Which of the following will not show geometrical isomerism? Which of the following will not show geometrical isomerism? Cr NH3 4Cl2Cl, CO En twice Cl2Cl, CO NH3 5 NO2Cl2, Pt NH3 twice Cl2. Please answer me this question. Please think and answer me this question. The answer is very simple and easy. Quickly give a choice. Please try.
Sir, is this option C?
Sir.
Very good. It is option C. Why it is option C?
Sir.
Metal
Coordination number.
A5 and B type. Now, coordination number is 6, no doubt about it.
Yes, sir.
But if you have a molecule like this, only one nitrite ion we have. All the other molecules are ammonia. All the other ligands are ammonia here. All right. So we cannot talk about geometrical isomerism here. All right. So if I have, maybe if I would have given you like this CO, NH3, 4 times NO2 twice, then you can tell this will exhibit geometrical isomerism. So MA5B type, they will not show geometrical isomerism. Even though they have a coordination number 6 and octahedral structure, they will not show geometrical isomerism, because I clearly told you geometrical isomerism is possible only for the different types of complexes. What are the different types of complexes we learned? We learned octahedral complexes having MA4 B2 type, MA3 B3 type, and MAA2 A2 type, A2 and EN twice. Only these kind of complexes will show cis-trans isomerism in case of octahedral complexes. The question they had given was MA5 B type. They will not show what? Geometrical isomerism. I hope you're following.
Yes, sir.
They're going very fast, or the speed is okay, manageable. I think we've
Sir.
done lots
No,
today.
sir.
Not manageable.
Sir. Sir, it's okay, sir. Understand.
It's okay. All right. One more question for today, and we will try to stop possibly. The third question, and to next class we'll continue. For square planar complex, a metal ABCD type, where M is the central metal, A, B, C, and D are monodentate ligands. The number of possible isomers. Number of possible isomers.
So 1.
No, how can it be 1? I can write metal. I can write A, B, C, D. This is the first isomer, square planar. The second isomer is, I can write metal. See, all are different now. This is, we can write B, D, C, and A opposite. And the third one, if you see metal, we have 4 isomers, B, A, C, and D. See, the arrangements are different. So therefore, they can have 3 isomeric forms. So the answer for this question is option 3. You see, listen to this. How do I write this? Now, how do I write this? This is the first isomer. The second isomer, you shift A here. B will come here. C will come here. D will come here. All right, we'll see. We'll write that. What will happen? What will happen, you see? What will happen now? So it is again a square planar complex. This is metal here. All right. So A comes here. B comes here. C here and D. Now you rotate this here. What will happen? The next isomer, what you will get? Metal, and you will have what? D here, A here, B here, and what? C here. You followed with this? Now you rotate this. Now you rotate this. What happens? The fourth isomer, what will happen if you rotate? Metal is here in the center. And if you rotate, C comes here, and D comes here, A comes here, and B. Now just observe this. A and B are on the same side. Here also A and B are on the same side. Can you see? C and D are on the same side. C and D are on the same side. B and C are on the same side. B and C are on the same side. Yes or no? The first and the fourth isomer looks same. That is why we say only 3 isomers are possible for the complex with tetrahedral square planar complex metal ABCD. Yeah,
Yes, sir.
understood or not?
Understood, sir.
Yeah.
Understood.
Ma'am, I'll stop the class, ma'am. Ma'am, if you
Yes, sir.
permit me,
Thank you,
I'll
sir.
stop the class, ma'am. Thank you, ma'am. Thank you, ma'am. Bye,
Thanks, sir.
everybody. Bye, bye,
Thank you,
bye.
sir.